Good evening, dear all. Let us begin today's class with the vector notation of Coulomb's law. As you can see here, we have a coordinate system of x-axis and y-axis with O as the origin. We have placed the charge Q1 at the position vector R1 arrow and Q2 at the position vector R2 arrow from the origin. Here we have the force F12, which is the force due to Q2 on Q1. We also have the force F21, which is the force due to Q1 on Q2. And you can also see one arrow which is denoting R21, which is the resultant of the two vectors R1 and R2 according to the triangular law. Now last year we had learned the triangular law that when we add two vectors, we definitely can find out the resultant of those two vectors by triangular law. So according to the triangular law, to make it simple, let us write R1 arrow plus R2 arrow, R21 arrow is equal to R2 arrow, as the triangular law says. The head and tail law also it is called. You can see the R1 is starting from the origin going towards Q1 plus R21 starting from Q1 going towards Q2. And according to the triangular law, its resultant is from the origin O to Q2, which is written here. From here, to make it simple, I can find out the value of the resultant vector, which is R2 minus R1. Similarly, the value of R12 can be written as R1 arrow minus R2 arrow, which means R21 is equal to negative R12, which means that the magnitude of R21 and R12 remains the same, but their direction is exactly opposite to each other. Now we come to the vector notation of the Coulomb's law. According to the Coulomb's law, as we formulated in the previous video, we have F21, as I said, is a force on Q2 due to Q1, can be written as K Q1 Q2 upon R2 1 square. Now our work is to write down the direction of this vector according to the vector rotation. So how do I write the direction of F21? I just write here R21 cap. Similarly, I can also write F12, force on the charge 1 due to the charge 2 can be written as again K Q1 Q2 upon R12 square. Direction of F12 arrow can be denoted by R12 cap. Now, as per the studies of last year, R21 cap and R12 cap are unit vectors. So, here we define unit vector as R12 cap is equal to R12 arrow, which is going to give us both the magnitude and direction, as is our knowledge, divided by R12 magnitude, such that we are only left out with the direction R12 cap. Similarly, we can also define R21 cap equal to R21 arrow divided by R21 magnitude. So I repeat here, R12 is the unit vector which is equal to the vector R12 arrow divided by the magnitude of R12 arrow. Similarly, R21 cap gives us the direction of R21 is equal to R21 arrow divided by R21, which we can replace here and find out, or we can rewrite F21 and F12 by this substitution. So, by looking at the formulas of these F21 and F12, we can again say according to R21 arrow is equal to negative R12 arrow, we can again write F12 arrow is equal to negative F21 arrow. What does this mean? That the mutual force on the charges Q1 and Q2 are equal in magnitude and opposite in direction because their position vectors as written shown here are in opposite directions. Now, as you can see, there is a diagram which I have placed for Q1 and Q2. Both are positive, so they repel each other. You can see both the arrows of F12 and F21 directed against each other. It means that they repel each other. Now, if I want to represent this type of a repulsion mathematically, how do I represent? I can represent it as Q1, Q2 greater than 0. When do I get Q1, Q2 greater than 0? Only if both the charges Q1 and Q2 are positive, or both the charges Q1 and Q2 are negative. Only then the multiplication of Q1 and Q2 magnitude can be greater than 0, meaning the answer is positive. What is the other meaning? If Q1 and Q2 are greater than 0, these forces are repulsive because these two charges are having same polarity of charges. That means both the charges will repel, and the answer which we get is repulsion. So you have to learn it as a complete package that if Q1, Q2 is greater than 0, it means both the charges are positive or both the charges are negative. Because these two charges are like charges, they will definitely repel. Similarly, now in this figure, I can see Q1 and Q2 towards each other. The forces F12 arrow and F21 arrow are towards each other. So how do I denote it mathematically now? I can denote it as Q1, Q2 less than 0. What is the meaning of less than 0? It means the multiplication of Q1 and Q2 is negative. It only means that one of the charge is positive and another charge is definitely negative. Only then their multiplication can be negative and their answer can be less than 0. It automatically means that these two charges Q1 and Q2 are attractive. So we repeat it as a complete package that if two charges Q1 and Q2 have opposite polarity, their product is less than 0, is negative. So both these charges will attract each other. We have another concept of equilibrium in a system of charges. So let us consider a system of 3 charges. When can we say that the system of charges is in equilibrium? As learned last year, a system of objects can be in equilibrium only if the net force acting on these objects or these charges here is equal to 0. So the moment we say that the system of charges is in equilibrium, it means that the force acting on these charges is equal to 0. Okay. So again, when we talk about equilibrium, once we get the system of charges, force F net is equal to 0, there are 2 categories of equilibrium: stable equilibrium, unstable equilibrium. Now you can see I have taken one system of charges in which it is said that it is in equilibrium. It means that F net is equal to 0. That has to be learned as a package. Okay. So what is stable equilibrium then? Now, simple example I am taking here. Suppose I shift this charge plus Q towards one of the positive charges and I leave it here in a new position. Will it remain there or will it go back to its original position? It will definitely go back to its original position because this is also positive. So two positive charges will never attract each other. So if I have left this plus q charge here, it will not get attracted to the other positive charge. It will go back to its original position. If such a thing happens after the equilibrium is attained, then that equilibrium is said to be a stable equilibrium, provided when we shifted the position of one of the charges and left it in the new position, it goes back to the original position. Then the system of charges is said to be in stable equilibrium. Now let us consider another example in which we have again a system of charges in which at the ends we have negative charges and in the center we have a positive charge of any magnitude. Okay. So now we are saying that the system of these three charges is in equilibrium. So automatically the net force on this system of charges is equal to 0. Now let us shift this charge towards the negative charge. Both these charges will attract each other because this is negative and this is positive. So what will happen? The moment I have changed the position of this positive charge, it will not go back to its original position. It will run towards the negative charge and come towards it. So what has happened? The system was already in equilibrium. When I changed the position of one of the charges, it did not go back to its original charge. It did not go back to its original position. It ran towards another position, new position. Then such an equilibrium is called as unstable equilibrium. So, if at all a body is in equilibrium, force net is equal to 0. It can be in stable equilibrium only if when changed the position and left it there, it comes back to the original position. The system is said to be in unstable equilibrium if I shift this position and it does not come back to its original position, then this system is said to be in an unstable equilibrium. Okay, so graphs of Coulomb's law can be studied in this section where we can use the formula of Coulomb's law of forces given by K Q1 Q2 upon R square. As is seen, or as the law says, F is inversely proportional to the square of the distance between the two charges. This is also called as inverse square law. Okay. Now, concentrate on this proportionality, which can be read in many ways. Let us read the first method. Force is directly proportional to 1 upon R square. Force is directly. If I use the word directly, then it is definitely proportional to 1 upon R square. So if I say that force is directly proportional to 1 upon R square, then I must have a straight line graph from the origin. So if I read this proportionality as force is directly proportional to 1 upon R square, I must have a straight line graph starting from the origin. Now let me read it as force is inversely proportional to R. As can be seen, I have put F on the y-axis and R on the x-axis. Then if that is the case, then I will not have a straight line graph because inversely proportional to R. Then how is my graph? My graph is a negative graph, but it is a curve. What does it show? That as the distance increases, the force decreases, but not uniformly. Similarly, if I read the proportionality as F is inversely proportional to R square, again I will get a negative graph, but it is a deeper curve. What does this graph say? Force is inversely proportional to r square. It means that as the square of the distance between the charges increases, the force decreases inversely. Okay, so in the exam, be very careful what is the graph asked. Is it between f and 1 upon r square? Is it between f and r? Is it between f and r square? You have to decide whether it is directly or inversely proportional and accordingly draw the graph. Force between graph between force and 1 upon r square is directly proportional. That's why it is a straight line graph, which is saying that as the value of 1 upon r square increases, force also increases. Okay, so let us move to the next graph, where again we are plotting the graph between force and 1 upon r square, which is directly proportional to each other. Let us plot the graph. The graph is definitely as a straight line graph, which is already explained to you. Going back to the formula, if f is on y-axis and 1 upon r square is on x-axis, then slope, how do we calculate the slope? F upon y-axis upon x-axis. What is my answer? F r square. From the formula, what will I get by multiplying f and r square here? I will get q1, q2. What does it mean? That this slope will give me q1, q2. Now, as I said in the previous section, q1 and q2 is in the positive quadrant. It means every point here is positive. That means q1 and q2 both are positive. What does this mean? The value of q1, q2 is greater than 0 and the force is repulsive. Agreed? So they can ask you in the exam that what is this kind of a force in the first quadrant, or what is this kind of a graph of f and 1 upon r square in the first quadrant of the graph. It is repulsive because my answer q1, q2 is greater than 0 in the graph. If q1, q2 is greater than 0, then the force between these two charges should be repulsive because both are positive in polarity. Now we move to the next graph, where again I have drawn the force on the negative y-axis and 1 upon r square on positive x-axis. Definitely I am going to get a straight line graph from the origin. But what does this quadrant say me? Or what does this answer give me? q1, q2 definitely less than 0, because every point on this graph will have x-axis coordinate as positive and y-axis coordinate will be negative. It means that one charge is positive, another charge is negative. So this line indicates which force? Attractive force.